In our part 1 video, I explained the concept of momentum and I introduced the concept of impulse, but I never really connected the two. So that's our goal for this video. In the previous video, we mentioned that if you change mass, you change momentum. But this time I want to consider a situation in which mass does not change, it's constant. So in that case, we can still change momentum by changing the velocity of an object. I want to go over specifically how we do that. How do we change velocity? Well, we know that we do that by applying a force. So let's consider the example of throwing a ball. From experience, we all know that if you want to throw it further, you throw it harder. So the amount of force you apply directly relates to the change in its velocity or the speed that it has when it leaves our hand. Okay, so let's make a new list of how to change momentum. And it's obvious that we can apply a force and we can adjust that force to control the change in momentum. Now I want to ask you a question though. Can you throw a ball farther with a full swing of your arm or just a quick flick? If you don't know the answer to that intuitively, just try it. Go grab a ball, or really any object will work, and try to do as a quick flick as hard as you can and see how far it goes. And then do a full wind up and toss the object and see which one you can throw farther. Okay, well, I'm hoping that you don't even have to do that. You just know that to throw the ball farther, you go for a full wind up. You know, there's a reason why pitchers will do that full motion when they are pitching in baseball. In this situation, you're not really adjusting the force as much as you're adjusting the time. You're controlling the time the force is applied. So I'm going to add to our list here that another way to change momentum is to change the time over which the force is applied. Okay, that's a separate quantity. Time is different than force, so we're going to list these as two separate options for changing momentum. Now we have another list of how to change momentum. Let's compare those lists. So we started with a list of how to change momentum by defining it changes in velocity and changes in mass. And then we just made a list that said we could also do the same thing by applying a force or changing the time over which the force is applied. Well, these are describing the same thing, how to change momentum, how to change momentum. So apparently the ways in which we change momentum, they must be related, and they are represented like this. Okay, here I'm describing the change in momentum. So I can change mass or I can change velocity. That's what this is saying over here. And on the right, this is the force that I've applied and the time. So if you multiply those two together, that ends up equaling any change you make to mass or velocity. And first of all, I need to emphasize that t here is what we call contact time. It's not just any time. So this is specifically the time interval that the force was actually applied. I'll use my example of throwing a ball to illustrate. Let's say I throw a ball and it travels 10 meters. Okay, so the time wouldn't be when I started throwing to when it landed 10 meters away. The time would only be that short interval in which I was actually holding onto the ball and going through my throwing motion. In the same regard, if I held the ball for 5 seconds before I threw it, I wouldn't include that 5 seconds in my contact time. So it's only when the force is in contact with the object and it's actually doing something. Okay, the other thing I want to illustrate or highlight is that this quantity is known as the impulse. So it's the force times the contact time. Impulse is defined as the product, meaning multiplication. So the product of the force on an object, if that force is changing the momentum of the object, and the time the force is acting on the object. The book talks about impulse quite a bit. I don't use it as much just because force times time is more meaningful to me than just calling it impulse. But it is, a well-known topic in physics, so I want to highlight that. I need to really point out, though, and stress that the impulse, you only calculate that or consider that if that force is changing the momentum of an object. So if the force isn't actually doing anything useful as far as changing momentum, then we would say it doesn't have an impulse. Here's an example that we've seen before. So this is our textbook just sitting on a table. This is an equilibrium situation in which the forces all balance out. So we wouldn't consider an impulse for this support force or this gravity because they're not doing anything to change the momentum, or in other words, change the motion of the book. Okay, well, when we do consider an impulse is like this example. So let's say the book was at rest and then I apply a horizontal force so that I start changing the motion of the book. In that case, because the force I'm applying is actually changing the motion, it's often called an impulse force. And then because it's an impulse force, we could calculate the actual impulse, which is the force I'm applying multiplied by the time in which I'm applying it. I should point out, though, that this is the time in which the momentum is actually changing, too. If I start pushing and then the book starts to travel at a constant velocity means no change in velocity, so I would no longer consider that impulse force or time of impulse. So this impulse would only be while I'm changing the speed of the book. Okay, so we have this relationship. This is called the impulse-momentum relationship. So impulse, momentum, specifically change in momentum. So the impulse is equal to the change in momentum is how you could say that. It's defined as force times the time, but it's equal to the change in momentum. Okay, so again, I want to go over why do we care? Why is this useful? So here's our throwing the ball example again. And from this relationship, what we can say then is that to get the largest change in momentum, we need a large force, or we simply need a force that's applied over a longer time period. So in this case, the wind-up doesn't really increase our force so much, it increases our time. So I'm going to state that formally as a force applied over a longer time will produce a larger change in momentum. In this specific example, it means that the ball will be going faster when it leaves the hand, which really means it's going to travel further. Here's another application of this force-impulse relationship. Okay, I'm showing a rifle and a handgun. Rifles and handguns can be made to shoot the same type of ammunition. When you do that, the rifle always gives a higher muzzle velocity than the handgun. That's the speed the bullet has when it actually leaves the barrel. So why do you think that is? See if you can think about why would a rifle result in a higher velocity bullet than a handgun, assuming they have similar rounds. Let's go into this. So I'm assuming they have similar rounds, which means they're going to generate a similar amount of force. Okay, so the force is going to be about the same. The difference is that, let's imagine this is a bullet right here, my red dot. And when the gun fires, that bullet is going to be pushed the length of the barrel. Then as soon as it leaves the barrel, that pushing force dissipates. So the bullet's on its own as soon as it exits the barrel. Right, now up here in the rifle, when it fires, it's going to create pretty much the same amount of force. But that bullet's going to be pushed over a significantly longer time, so that when it leaves the barrel, it's simply going faster. It's just an application of our impulse momentum, same thing as throwing the ball. So in this case, a force applied over a longer time will produce a larger exit velocity. It was the same thing for our hand, if we call that an exit velocity. Now, do you remember our frog friend? And I asked the question, why does a frog have long legs? how would you answer this question now using our impulse momentum relationship? All right, well, I'm going to put the same statement up there. A force applied over a longer time will produce a larger change in momentum. So the legs of the frog can generate a certain amount of force. Okay, that's just the biology, the mechanics of the frog. But if the frog can apply that force over a longer amount of time while it's in contact with whatever this is, then it's going to have a larger change in momentum. So in this case, that means that the frog will be traveling faster after a jump, which in turn means it will jump farther. Why is that good for the frog? Most distinct physical features in the animal world have something to do with giving them an advantage for surviving. So if a frog can jump farther, you would imagine it has an advantage for catching prey or escaping predators. I found this cool slow motion video of a frog jumping. Watch how it really extends that contact time during the jump. This time I want you to watch its landing. See how it stretches out its arms right before it lands? Why would it do that? It's the same principle, just a different application. So I'm going to take this equation up here and I'm going to rearrange it with algebra to solve for force. So now time is in the denominator here. So what that means is if you apply the force over a longer time, then you'll have a smaller force. So if you watch the frog here, the frog's extending the time in which the momentum is changing. And that's important. The momentum is going to change regardless of what the frog does. It could happen fast or slow. The frog just makes it happen longer or take longer time. The benefit to the frog is that it has less force that way, so it's easier on the frog itself. The statement I'm going to make from this observation is that a change in momentum that happens over a longer time will result in a smaller impact force. As human beings, we understand that just intuitively. When you watch a simple animation like this, now, there's many things that look wrong with it, but one of the biggest things to me is that the way my figure landed. Nobody ever drops off a ledge and lands with their legs straight like that. We know just intuitively that we should bend our legs. So why do we do that? Well, it's just like the frog. We're increasing the time in which we're changing our momentum, which decreases the force that is applied to us. It's the same principle going back to our water barrels. The same principle is applying here. If you can increase the time in which the car has to go from some speed to zero, then you decrease the force, the overall force that's applied to the car. In a different modern application, notice here I have an old car. These old cars have very rigid, very stiff frames. And there was an advantage that they were kind of like tanks in that sense, that they could crash into something and not have a lot of damage. Today's cars, however, have what's called a crumple zone, in which they purposely crumple in a collision. Now, why is that useful? It's the same principle. A change in momentum that happens over a longer time will result in a smaller impact force. So if you can increase the time in which you slow down, even a fraction of a second, you decrease the force and therefore decrease the potential damage to the passenger. The other thing you're seeing in here that uses the same principle are these, the airbags. They have the same purpose. They just try to increase the time over which you slow down or you change momentum. So airbags are using the same principle. Let's go through this example using some real numbers. And what I want to solve for is the force that this Honda Civic experienced, what we're going to call is the average force that the Honda Civic experienced during its crash. So to do that, the first thing I need to do is figure out what its momentum change was. So I take the final momentum and I minus the initial momentum. Well, the final momentum is going to be 0. The car crashes and comes to a stop. The initial momentum, I had to look up some values. So I found that the mass of a Honda Civic is about 1,200 kilograms. And I assumed a certain speed here. I couldn't find the exact value for this picture, so I just made an educated guess. 20 meters per second is about 40 miles per hour. All right, now with these values, we can just plug those in and we find that the change in momentum was negative 24,000 kilogram meters per second. The negative, I need to point out here, all this is telling us is direction. So it's not necessarily all that useful for our purposes right now. What this means is that the force, when I plug the change in momentum up here, the force is going to be negative. And all that's really saying is that the force is in the opposite direction as the original velocity was, which makes sense because that's why it slowed down. Now I could have gotten rid of this negative sign by simply saying that the original velocity was in the negative direction or left, and then that would have made the force positive. The real point to all that is just that the force is in the opposite direction. So I'm going to kind of ignore that negative sign for now that I've explained why it's there. Let's calculate the force, but I want to first consider what if we don't have a crumple zone. So one of those older cars with a very hard, rigid steel frame. I need to calculate the change in momentum and time. And so I used the mass and speed of the Honda Civic, and assuming it just didn't have a crumple zone. And I had to make an educated guess on time. Again, I didn't find exact values for this, so I just tried to estimate the best I could. All right, well, if I figure out what all that is, it's 120,000 newtons. That's a lot of force. The units, when these all combine together, it gives you newtons. Okay, now let's consider with a crumple zone. The change in momentum is going to be the same. I mentioned that earlier. If it has the same speed and the same mass, then it has the same change in momentum. What the crumple zone does is it increases the time over which you slowed down. So in this case, I assumed it was 4 times longer. Notice that 0.8 seconds is still really fast. I mean, this collision is going to happen quick. What that gives us now is 30,000, which is significantly less than 120,000. In fact, it's exactly 1/4 of 120,000. By increasing my contact time by a factor of 4, I decreased the force by a factor of 1/4. So I ended up with 1/4 of the force by increasing the time by a factor of 4. Another way to say that is simply, if I make the crash 4 times longer, that results in 4 times less force. It doesn't really seem like much when we're just looking at raw numbers, but think of it this way, okay? So imagine you're gonna get punched in the face, all right? You don't have a choice, it's gonna happen whether you want it or not. You do have the option, though, to either be punched with a certain amount of force, or you can choose to be punched with 4 times less the force, or 1/4 of the other option. You know, when you look at it that way, nobody's going to take the first option. This is the advantage to a crumple zone. I also want to highlight that we could have reduced this force by reducing the mass. Now I don't really see a practical way of doing that, but you can imagine if somehow right before the crash the car could ditch 1,000 pounds, that would have made a significant change to the force needed to stop it. Again, it's not really practical, but it is interesting to consider. Okay, so I want to look at one more situation here and see if this is making sense. So try to answer this question and really take it seriously, because this is going to really test how well you understood this. Imagine we have a heavy truck and it crashes into a small car. Which vehicle had the largest change in momentum? I'm going to give you a little bit of time. I want you to really think about this one. The answer is neither. They had the same change in momentum. It's common for students to miss this question in an introductory physics class. Our intuition sort of tricks us in this problem, and I'll try to explain why. Remember, I asked a very similar question in our previous video about Newton's third law. In that case, what I said was a heavy truck smashes into a small car. Which vehicle experiences the largest impact force? And the answer was neither. They had the same impact force because of Newton's third law. So that states that every force has an equal and opposite reaction force. And that's the same in this situation. So the truck and the car both experience the same force. That also means that the time over which that force was applied is the same because it's called contact time. If they lose contact with each other, then they're no longer applying forces, and so the time's got to be the same as well. All right, so we can state that the contact time of the impact force is the same for both. So now we have equal force and equal contact time. Well, that's just what we call impulse. So again, if our force is the same and our time is the same, then they have the same impulse, but impulse is equal to the change in momentum of the object. So they must therefore have the same change in momentum, which brings us to why the answer is neither. They have the same change in momentum. This question is commonly missed by students in introductory physics, and it's an issue that our intuition is fighting this concept. Here, I'll try to explain with this question. All right, same crash. Now the question is, which vehicle had the largest deceleration? What do you think the answer is in this case? This time it is the small car. Let's go through that. Okay, this is our same relationship. And we just talked about how the impulse was the same for both, which means that this total quantity, the total change in momentum, has to be the same. But individually, we can fluctuate mass and velocity all we want, as long as when they're multiplied together, that total quantity is equal to this over here. In the case of the small car, it has a smaller mass. So that means that to get the same total quantity, the car must have a larger change in velocity. Notice this is change in velocity, not velocity itself. Okay, a change in velocity is just what we call a larger, an acceleration. So a larger change in velocity is just a larger acceleration. For this problem, I called it a deceleration just because that's what people commonly say. But remember, it's an acceleration is any change in speed, so that includes slowing down. This discussion should seem familiar. In our previous video, I gave an example of a dragonfly colliding with the truck, and it was a very similar situation, and I explained that it wasn't really the force of impact that caused the damage to the dragonfly, it was the acceleration, the very large acceleration of the dragonfly. It's a similar situation here. The larger acceleration of the car is going to result in more damage. We certainly would expect more damage in the smaller car. Think of it this way, structurally, the car has to withstand that change in velocity, and there's just not enough strength there to do that, so that's why it results in more damage. You know, it's not that force doesn't ever play an impact. For example, you know, if you take an object and you apply a force very slowly, if it's strong enough, you can still crush that object. So that wouldn't be an acceleration issue. That would be force, which is what our intuition tells us. So it's understandable that this is a confusing issue. And in some ways, from a practical standpoint, it doesn't really matter whether you understand the damage is caused by the acceleration of the force. It's going to happen either way. But you know, if we really want to describe motion from a mathematical standpoint, we need to be able to distinguish between the two. This is a natural spot to take a break. In our next video, we'll discuss conservation of momentum.